Yes. So okay. So we were here at morning. Now we want to design the controller for this converter. We will cover as far as possible. There are a lot many slides. So okay. So the buck converter, why we will use that, we are clear with that we will be using, because this will show the steady state error. So we want to eliminate the steady state error, and then we will do through this uh, controller design. So our purpose here is that this is our original transfer function GC. It is obtained to us, and this also includes 1 upon Vm. This its transfer function is 1 upon Vm, and we assume that Vm is equal to 1. Let's say it's unity only. Okay, so this is our uncompensated transfer function, and this is the PI controller's transfer function which we want to implement. Right now, as we said that after closed loop, our loop transfer function will be GC, GS, and GPWM of S. We go to this block diagram. Then from this block diagram, this GC, if I erase all link on this slide. So on this will be in cascade. So if we consider VS W and peak voltage of the Sawtooth waveform to be 1, then this will be unit, right? So yeah. So now for this transfer function, we need to design this PI controller. So our closed loop system's characteristic equation will be 1 plus GC into GS. Now this characteristic equation will be 1 plus GC GS equal to 0. But if we want that, we need certain phase margin and gain margin. Let's say A is the desired gain margin, and phi is the desired phase margin. Okay. So we define this E minus J phi, E minus J phi as a gain phase tester. Gain phase tester. Gain phase tester. Okay, so we take this gain phase tester as E raised to power minus J phi into A, right? A is also there. So we add this in cascade with this, right? So our new characteristics, desired gain margin and phase margin will be this one. So what does it represent? If let's say phi is equal to 0, phi is equal to 0, it means this is phase margin is 0. So when phase margin is 0, then system phase is, what is the system phase? The phase margin is defined as 180 degree. What is plus these are one system phase. System phase is the line which this phase plot should cross. It means whatever gain is there at that moment, that is called gain margin. So A is there. Or if I say A equal to 1, what is the A equal to 1? This is the line at which gain plot is crossing this horizontal axis. So at this, whatever is the phi, that is the whatever is the phi, means 180 plus system phase, that is the phi. So that's how this gain phase tester is defined. Now, this is our equation. If this equation is satisfied, then we can say that our KP value, whatever value for KP and KI is satisfied, that PI controller satisfies this gain margin, phase margin. So that is now let us find at what value of KP KI this gain margin, phase margin will meet. That is our motto. So this is what we do in this equation. in this equation, we substitute these things. So this will be 1 plus a e raised to power minus j phi, which I can write as a cos phi minus j sin phi. What is gs? Gs is v1 j omega plus v naught on a2s square. So that is minus omega square plus a1 j omega plus a naught. Okay, so gs, and what is gcs? kp j omega plus ki upon s. That should be 0, right? So this is the equation. Now we can do, we can simplify this equation, or okay, s also we put j omega only, right? So we simplify this equation, and after simplification, we can, segregate it in two parts. One is real part, another is imaginary part. That will be equal to 0. Time is less, so I'm not going to do that calculation. If I segregate it, so the same equation is written here: 1 plus a e raised to power minus j omega gs gcs. Okay, so this values we have put. Now we simplify, so we'll get two terms. One will be the real terms, another will be the imaginary terms. So this, let's say this is real terms, this is imaginary terms, equal to 0. Now within real term also we will have, because kpki will be there, so we have some coefficients of kp, some coefficients of ki, and there will be some coefficients which is independent of kpki, right? So three terms we are having. First term is the coefficient of kp, another is coefficient of ki, and third one is constant only. Similarly, in this side also, imaginary side also, some is coefficients of kp, some is coefficients of ki, some is constant, right? Now what we will do, so this what is kpki is okay. What is this re1, real 1, real 2, real 3? That we have written here. That we have written here. Re1 is equal to a minus omega square v1 cos phi plus omega v naught sin phi. Re2, re3, im1, im2, im3. So these all terms have been obtained in terms of these converter parameters b1, v naught, a1, a2, like that. Another is that omega, which is the frequency. Third is the phi, which is known to us. This is the phase margin. A is the gain margin, which is also known to us. So here, except omega, everything is known to us, right? So next step is that we will, we will separate out this kpki. We will separate out this kpki. So kp re1 plus ki re2 plus re3 equal to 0. So we im2 simply im equal minus im3. Okay, so one equation we are getting from here, another equation we are getting from here. Now these two equations we can simplify for kp and ki. We can simplify for kp and ki from here, these two equations. So this kp will be function of re1, kp will be function of basically this re1, re2, re3, and im1, im2, im3. Similarly, this ki will also be function of all these terms. Right? And we already know that R, E, and IMs are different terms of non-variable in which omega is the unknown. If we put all those things, then we get these expressions, separating real and imaginary part and simplifying for Kp and Ki. What we get? Kp omega phi is equal to this new terms, where we have again defined these some variables Q3, Q2, Q1, Q naught, P2, P naught. So Q3, Q2, Q1, Q naught, P2, P naught. What we see, all these terms are function of A1, A2, A naught, B1, B2 only. These are function of, and these are the transfer function parameter. So it means all these things are known to us. All these things are known to us. Okay. Now what about other terms? Other terms is sine phi. Sine phi is means phi is known to us. A is known to us. Right? Everything is known to us except omega. Here omega is not known to us. Omega is not known to us. Omega is okay. I should write comma A also. So this Kp is function of omega phi A. Ki also function of omega phi A. It means if I know omega and A, I know phi and A, and if I vary omega, then a different value of omega, let's say I put some omega equal to omega 1, then it will be Kp1, Ki1, some combination will be there. Omega equal to omega 2 is there. Then this is Kp2, Ki2. Omega equal to omega 3 is there. Then this is Kp3, Ki3. Like that, I will get number of pairs of Kp Ki given omega 1, omega 2, omega 3. Okay. So what we do, and you all know that this A and phi will not appear together. Whenever we put phi equal to 0, then A will exist, right? And for the simplification, we have considered it to be together. But whenever phi is 0, then only A will be there. And whenever A is 1, then only phi will be there. So what we can do when we are designing this PI controller for, let's say, for desired gain margin, then we put phi equal to 0 in these equations. So that time we will get Kp, which is function of omega A only, Ki, which is function of omega A, function of omega comma A. When we need desired margin, that time we put A equal to A, right? A equal to A, and it will give T in terms of omega phi, Ki in terms of omega. Is that okay? Now, so in this way, we will get locus. For this, if I vary the omega, if let's say I want to plot Kp versus Ki, if I plot omega, I'll get like this. Similarly, if this is Kp, this is Ki, for it, I will get one more locus for given phi. For given phi, so I will get two locus. But normally what happens, as I said, in our buck converter and DC to DC converters, we have infinite gain margin. So we do not worry about gain margin only. We just worry about phase margin. So when gain margin requirement is not there, then we do not need to plot this boundary locus. And we do not need this boundary locus. And only we need this boundary locus, which is for desired phase margin. So what is this basically stability boundary locus, which we are discussing? By varying omega, we obtain two boundary locus in KPK plane. For a specified value of phase margin, is desired phase margin, the boundary locus is obtained by setting A. It means, let's say, So let's say I have this boundary locus. It is for, this is your Kp, this is Ki. It is for desired, first one, let's say desired phase margin. So we put A equal to 1 over here. It means this boundary locus, what is the stability boundary locus means that if I take, so all these points are obtained by varying the omega. That's why you will get this locus, right? Now, if I choose any KPK, which should be positive, maybe because this is just mathematical expression. So mathematical expression can give you some combination of KPKI, where K, P or Ki may be negative, and also satisfy the equation. Then we need not to take care. We need not to consider such pairs of KPKI. We just need to keep KPKI which is positive only, right? Okay, so if I choose any value of KPKI within this boundary locus, so that will guarantee me that my system is having at least 5 phase margin. Let's say 5 value is 60-degree we designed for. It means if you take any KPKI within this boundary and implement that, then your system will be having phase margin of at least 60-degree. It may be more, but at least 60-degree, right? So this is the boundary locus. If you take outside this, then it will be less than 60-degree, right? Similarly, specified value of gain margin A. If you want that I should have some gain margin A, then we set phi equal to 0, and again by varying the omega, we again plot. So definitely for we put phi equal to 0 and put A equal to 2 something. Let's say we need at least gain margin should be 2, right? Or 1.5 or something else. Then it means the Kp and Ki will be obtained in those conditions that will be different. So let's say this is the boundary locus which is for desired gain margin, and we set for this phi equal to 0. Okay, so if I take any value of KPKI within this stability boundary locus, that will ensure that my gain margin always will be greater than or equal to A, right? So individually they will be like that. But if I want that my system should have the phase margin of at least 5-degree and gain margin of at least A, then what I need to do? I should, in that case, take the whatever overlapping area of both, because this is for phi margin, this is for A. So whatever is overlapping area, this overlapping area, A. This overlapping area will ensure that your gain margin, this overlapping area will ensure that if you choose KPK within this, then your system will have at least a gain margin and at least 5 phase margin. At least a gain margin and 5 phase margin. So we can choose. So that's what the intersection of these two boundary locus gives the desired stability regions, which guarantees the specified phase margin and gain margin. We can choose a combination of KB, KP, KI, which should be obviously positive within this stability region. DC to DC converter applications normally not phase margin. This is gain margin. Gain margin is infinite, therefore only one boundary locus is sufficient to ensure desired phase margin. So This way we can find out Kp and Ki. Let us take one example. We take one example. So here we consider that our input voltage is varying. This is a buck converter example between 20 to 24, and this nominal voltage is 20 volt. The desired output voltage is 12 volt. Load is 11 to 22 ohm, and our nominal is 11 volt, 11 ohm, right? Then this is the non-ideal parameters. That is okay, right? Now switching frequency we have taken, let's say 10 kilohertz. Now yesterday we have seen that by putting these values we get this transfer function. And we considered Vs equal to 1. Our uncompensated DC to DC converter transfer function is this one, right? So this is GC, and this includes PWM, this T. This T includes PWM as well as the Planck. Now our target is that in order to follow this V reference, right, we need to design GCS, which is PI in our case. So actually, let us come to this first. Yesterday we have seen this transfer function of this. How to obtain this transfer function and its Bode plot. If you see, it is blue one. Blue one is the Bode plot of that transfer function, which is uncompensated. And we observed that this original system. So today we learned about Bode plot also. So this was blue. I am focusing on blue one. This blue one. So this is the magnitude plot and this is phase plot. And is having constant gain in low frequency region. It is sure that this kind of system will have steady state error, and that we have observed also. And apart from that, this is the point where we are having gain crossover frequency. And at this gain crossover frequency, what is the phase of the system? So we see here it is just some minus 154, right? That's why this uncompensated system, this is a non-ideal. So uncompensated system was having a phase margin of 26 degree only. So this phase margin is about 26 degree. Okay? And what about the gain margin? So if I look for gain margin of blue, then it is never crossing. Sorry, we go for here. So this is settling to minus 90, right? It will never cross minus 180 degree. If it never cross, it means it will cross at infinite. So what will be the value of gain over there? Infinite. So gain margin we are not worried about. Only we are worried about that this phase margin should improve. This phase margin should improve. Now, if you look for this green, right? So this green one is the Bode plot of PI controller. This green one is the Bode plot of PI controller. So in this green, what we see that this Bode plot is always introducing. This Bode plot is always introducing a negative phase, and this value is around, I think, 2 kilohertz. Now, what is our crossover switching frequency? 10 kilohertz. So what should be our gain crossover frequency? 150 to 110. So 1 kilohertz to 2 kilohertz, right? It was more than 2 kilohertz. Definitely, I cannot go beyond this. I have to back. So, and this system, green one, PI controller, if you see its phase plot, then it is always introducing minus 90 degree, right? And if you see here at this point, after this, it is negative at around 0. I will not go here. If I come back, then I have to see that whatever gain margin I am required from the compensated system, that should be available with the system, right? Blue one I see, then okay, beyond this point, you see that there is a lot of phase margin available. If I shift this float to the left, then here there is no issue. Here there is no issue. It can compensate. Even if you see in this region, then also we can get 90-degree phase margin, right? Something 180 minus 90. So that is safe area. That is safe area. It means if I come here, then it is safe area. Now, accordingly, I can say that my gain crossover frequency is here, and it may, but the only issue is that if I'm going beyond this point here, then my crossover frequency is reducing. Phase margin is sufficient one, but if I take this 90-degree to be phase margin, then this is sufficient one, but crossover frequency is very less. It is raised to power -1, which is 100. It's 100 hertz. So below 100, if I go, my system will be sluggish. Beyond 100, if I go, then what happens? My system is not allowing to have me more phase margin. So we have to choose some optimum value. So let us. So this decided, along with this decided that okay, PI controller has one pole. So you can see this green one, this area. This is having one pole, and if it is added, then overall system will be having -20 dB per decade slope. Okay, so that's why we went for PI controller. Now let us. So this we have seen its Bode plot. Now for this, so this is our B1S plus V node upon A2S square plus A1S plus A node. This transfer function is there. So for that transfer function coefficients we have obtained, we got just different equations. In those equations we put these coefficients. Now to 1. So this A will not be there. It is 1. Now these are the two equations, and let us consider value of phi. Phase margin required is 75 degree. If I put this 75 degree over here, then this also becomes constant. Only thing remains is omega q, omega square, omega, and this will become constant. Here you put value of omega, this will be constant. Sorry, you put value, so this will be variable, this is constant. Only it remains function of Kp remains function of omega, Kp and Ki both. Once phi is fixed. If phi is fixed, Kp and Ki remains function of omega. So the same value of omega, we will have Kp Ki. So that's what we did. We just wrote one program in MATLAB. We increased the value of omega from, let's say, 0 to some value. Keep on increasing. When it touches this value, Kp and Ki, we plot it. Right. We got this locus. We got this locus. And this locus is called boundary locus. So within this locus, whatever value you choose of KPKI, that will satisfy that particular equation. That will satisfy that particular equation. Now we know that if okay, so if what I see here, if I choose any value here within this, then that will give me gain margin of at least 75 degree, at least 75 degree. So sorry, phase margin of at least 75 degree. And in all cases, this phase margin will be greater than 75 degree. Right. So what we observe here that some of these values here, this is negative. This is negative. These Kp values are negative. Ki are positive. So if we put an equation, then this equation will satisfy for this mathematically. But if you realize any this Kp upon Ki upon S, so to realize this PI controller will be difficult, will not be practical. So we choose just positive value only. So we choose just positive value only. So we take any positive value. So we take any positive value in this first quadrant, right? And that value will be able to give me at least 75-degree phase margin. And let us choose, we have chosen this value, Kp equal to here, this is 0.202 and Ki is 20, Ki is 20. So this Kp Ki I have obtained. Now I put this Kp Ki, so my transfer function becomes Kp plus Ki upon S. 0.02S plus 20 upon S. This one. This is PI. Now, what is my loop transfer function? Compensated loop transfer function. I say compensated. Compensated loop transfer function. So this compensated loop transfer function becomes this GCS on 0.02S plus 20 upon S into that second order transfer function. This is T1 of S. Whatever that second order transfer function was there, numerator, denominator. If I take now this to be a new system, and if I plot it, it's body plot, then what do I get? I get this red one. I get this red colored body plot. So magnitude plot is this one. This is the phase plot. So we see here that this compensated system is having now minus 20 dB per decade slope. So this slope ensures me that in low the systems, but that makes sure that steady state error will be removed. Steady state error will be removed. Now, what about the phase margin? So this is the point at which gain curve is cut, and when then this gain curve is cut, then that decides the phase margin. So it is at this point. So at this point, the system is having about a minus 80-degree phase. So the phase margin will be 180 degree plus system plus 73. It's a 73 around, not 83, 73 around. So this will be 107 degree. Phase margin is 107 degree. This is definitely greater than 75 degree. So whatever phase margin I have obtained from the compensated system, that's the correct only. But some another issue has been created. What is that issue? So we'll see here that now crossover frequency is just 50, not 50, let's say 56 hertz. This is just 56 hertz. It is far below than the what we wanted, 1/10, 1 kilohertz. What will be the impact? Your steady state error becomes 0. It will follow. It will follow this steady state error 0, right? But the time to track this, that time will be large enough because gain crossover frequency has been reduced. And there is no way, no other way. There is no other way to, thoda sa little bit margin we had over here. If you go this way, then we could increase phase margin also. And so this region we have randomly selected any value, but we could do optimization also within that, and we could find any other value also, this value or somewhere. So somewhat this steady state, this gain crossover frequency could be increased. That was possible. That was possible within this PI controller only. We need to find out any other value. So, okay. So the drawback is that this omega GC has decreased. So system becomes slow. System becomes slow. Now, this is from simulation point of view, from analytical point of view, control point of view, we have studied. Now let us see how does it impact on the real system. So we have applied this particular controller, and now we are changing the. So first we are taking results with reference voltage variations. So as I said, let's say keep the resistance and this VG to the minimum values. This minimum load, that is the worst condition, minimum input, maximum load that we have taken. And now we are changing reference from 12 volt to 9 volt, 12 volt to 9 volt. So what we see here, okay, when we are changing this reference voltage, then at this time, this is the reference value at this time 0.24. This reference voltage is changed, and when this is changed, then this is the load current and this is the output voltage. So this was 12 volt, this was also 12 volt. Now this has become 9 volt. So this reference must follow 9 volt. It is following also, but it is taking some time. Similarly, if this reference voltage is increased from 9 to 12, then it is increasing 9 to 12, but it is taking some time. And this time is taken because the PI controller has low crossover frequency, low gain crossover frequency. So in order to, okay, let us see what is the impact on other things. So if I change the reference, okay, so this was the condition when I have taken full load. Now, when I change it from 12 to 15, my nominal voltage was 12 volt, and if I'm changing it 12 to 15, then what happens? So if I'm changing 12 to 15, then also it is giving me satisfactory result. The only issue is that it is taking certain time to get settled. So that is obvious, but steady state error is 0. It is tracking the reference. That is the point. So these are some other cases when we, whenever you design any controller for a converter, then these are the three cases we always should consider. One is variation in reference, another is variation in input voltage, third is variation in load. And whenever we are considering any one case, then other two should be kept constant. It means variation in other two should be kept constant. So like here, we have kept V0 to be 12 volt, right? V0 to be 12 volt. And this is the R which is kept now full load. It is not varied, but we are changing on input voltage variation. So when we are shifting 16 to 24, then we are getting some overshoot are there, but after some time it is getting settled. And same is observed in hardware. So this spike you can ignore because this spike is just we were changing this voltage using some mechanical arrangements, electrical arrangements only, but it was not fast switch. So we were not having that programmable power supply. But if you have programmable power supply and you change it in this way, then you can easily see that this voltage is being tracked. Okay. Secondly, we observe this output voltage when input voltage is shifting down. Earlier we observed when it was up. Now if voltage is down, then what happens? So if voltage is down, input voltage is down, So you can see that initially this output voltage is trying to get down and down, down, down. Obviously, it could have settled to some this value. But because now we have designed a controller, if there was no controller, it could have settled to this, and then this much will be the error. But because we have a controller, so controller acts, and this controller helps us. This controller help us to track the output voltage back. To track the output voltage back. So here also we see. Similarly, you can see in hardware result also. The another is when load is half. So now we kept load to constant at half of the value. Obviously, B output reference is constant 12 volt, and then we stepped up. So we are giving a unit step to voltage. So here also, when it increases, it tries to increase. Push up for some time and tracks back and tracks back. Same is here. And this is 22 ohm. This is 12 ohm. So if you set 12 upon 22 ohm, so I naught settles somewhere here 0.545, right? Now this is step down again at half load, step down. So if it is stepping down, output voltage will try, but because controller is there, so it will again settle it back. Same we can see in hardware. In all the cases, we have seen that whether it's a reference variation or it is an input disturbance, but this controller is tracking. This is due to this negative feedback only. But it is taking some time. The reason behind to take time is that this low bandwidth or low gain processor frequency in case of this PI controller. So now the third case, case 3, is the load variation. Okay, so I have to finish next 2-3 minutes. Okay, so in that case, I have kept VG to be constant at input voltage to be constant at output voltage to be constant at 12 volt. Now we see this is kept constant, and only load is varying. So load is varying. So it is half to full. Earlier R is equal to 22 ohm, and this is at 11 ohm, right? This is 11 ohm. So what is happening? Load has increased. If load has increased, output voltage is decreasing. It's trying to decrease here, but due to controller, it is again reaching here. Due to controller, it is reaching again here. The same observations we can see in the output results. Now this is the load variation. When input voltage is set to maximum, then also we can see this load is increasing. So voltage is to go down, but because this is the controller design here, so it is tracked back, but it is taking certain time. Okay, so here what we have seen that in all the cases, this buck converter helps us. And this PI controller helps us to track the output voltage, right? But it takes some time, sluggish time. So quickly, in 2 minutes. So in order to compensate these things, this sluggish nature of this, what we do, we have designed one PI lead controller. PI lead controller. So what this PI lead controller basically, so we replace this PI controller with the help of PI lead controller. So what this PI lead controller basically does, it increases the gain crossover frequency while introducing a slope in the DC region. So this is the PI part and this is the lead part. We combine these two and we get new controller, that is PI lead controller. So we set these values, and what we'll observe that here, this is our uncompensated system having 26-degree phase margin. So we design this PI lead controller to obtain phase margin of 75-degree and crossover frequency of 2 kilohertz. So you can study this in one of my paper. This algorithm is given. Uh, So this is our PI lead controller transfer function. And what you are observing here, this blue one is the earlier one, same as previous one. Now green one is the PI lead controller. TI lead controller, and the red one is the compensated systems overall body plot. So here what you seen that here in red one, this red graph, there is minus 20 dB slope, which takes care of the steady state error. And here if you see that this point, this is gain crossover frequency. At that frequency we find the phase margin also. So good phase margin. So at this crossover frequency there is good phase margin, 75-degree phase margin. And now this phase margin, if we implement this, then you can see that here there is no much delay. It is tracking well. Why? Because now you can see here when I'm changing the input voltage, then there is no much overshoot, no much delay, right? In all the results, right? This is happening. Why happening? Because we have now taken care of the crossover frequency, right? So you can see here the results. Okay, so talk. So I stop my talk over here. We will reach maybe in next session or after 4 o'clock. You can have 2 minutes break if you need, or we can continue it. So, sir, can we start your introduction again?
Yes, Manmohan, start.
Okay,
Should I start?
Sir, just 1 minute, please give me.
Okay.
I just introduce you. So, good afternoon, sir, and dear participants. We are very fortunate to have sir with us. So, Professor Mukesh Kumar Pathak, sir, from IT Roorkee with us for this talk on solid state transformers. So, I just introduced sir is my supervisor as well, a PhD supervisor, and sir has done his MTech and PhD both from IT Delhi, and sir has been with IT Roorkee for last 18 years. So he's a professor over there, and just now, like a couple of months ago only, he relieved from the duties of head of department of the institute. So sir has many projects, papers, research papers. He has guided many PhD and MTech theses, and actively involved in various projects at IIT Roorkee and research in pilot and converters, these solid state transformers, inverters, etc., power quality. So we are very fortunate to have sir with us and enlighten us with his knowledge on this domain. So we welcome you, sir. Over to you, sir.
Okay, thank you, Manmohan,
Yes, sir.
for introduction. And I'll now start. I'm sharing my screen. Please let me know if you are able to see it. Share.
Sure, sir.
I've shared my screen.
Sir, it's not visible as of now.
Okay. Let me do it again.
सर आपका स्क्रीन तो आ रहा था बट पीपीटी नहीं आ रहा था
अब हो
स्क्रीन
रहा
में
है?
सर अभी आ रहा है फुल स्क्रीन यस सर
अभी आ रहा है?
यस सर यस सर यस सर
Okay. Now, can you see it?
यस सर प्लीज मेक इट फुल स्क्रीन सर
Full screen किया मैंने.
सर यहाँ पर फुल स्क्रीन वाला नहीं है वो स्लाइड शो में सर स्लाइड शो में जाके
Full screen तो किया.
स्लाइड शो सर
अब
सर अभी भी नहीं दिख रहा है स्लाइड शो में
ठीक है, मैं दोबारा शेयर करता हूँ. फुल स्क्रीन शेयर करता हूँ तब आएगा शायद में. अब देख पा रही?
हाँ सर अभी सही आ रहा है अभी सही आ रहा है प्रॉपर परफेक्ट
अब
या इट्स परफेक्ट
स्लाइड चेंज कर रहा हूँ. चेंजिंग
सर या
स्लाइड्स आर
इट्स
चेंजिंग.
हाँ इट्स मूविंग यस सर परफेक्ट सर
I hope I'm also audible.
Yes, sir. Properly audible. Everything perfect.
Okay. So thank you very much for giving me this opportunity to talk to you. I'll give a presentation on solid state transformer for green energy, which I think is also green energy. This course is about green energy. So as we see today, the renewable energy scenario in India is fast changing, and as of today, as per Ministry of New and Renewable Energy, we have crossed the milestone of 100 gigawatt of renewable energy installation. So the capacity of renewable energy sources, installed renewable energy sources in India is now more than 100 gigawatt. And as things stand, we are at fourth position in the world in terms of total installed capacity of renewable energy. Solar is fifth, and for wind we are at fourth position.
Sir, you are audible. No. Okay, fine, sir. ठीक.
Hello?
It's audible. It's audible.
Hello?
It's audible, sir. It's audible. Yes, sir.
Okay. So now there is a push for this more renewable energy installation, and 50 mega gigawatt is under installation. So that will make it 150 gigawatt very soon. And 27 gigawatt is under in the process. So overall, we are, the country is aiming to achieve a renewable energy installation of 450 gigawatt by the year 2030, which now seems to be, quite, uh, achievable. This, continuous integration of renewable energy into the power system is bringing a lot of challenges. And the challenges are a lot of, power quality issues, energy storage, battery energy storage, control of these renewable energy sources, and overall stability of the system. Uh, Solid state transformer is a kind of transformer which can provide a solution for many problems that renewable energy systems bring in. So this presentation is about, we'll discuss how the solid state transformer and see how the solid state transformer can be used, how can we make use of these new technology for better integration of renewable sources and better control of these sources. So we'll introduce solid state transformer. We'll also see the new type of devices, wide band gap devices, and their converters for the renewable energy, uh, SSTR, solid state transformer architectures. We have developed few prototypes. We'll also look at that. And solid state transformer is primarily, it comprises of high frequency transformer also. So we'll also look at the high frequency transformer design if time permits, and more topologies of SST, and then the future direction. So, role of SST in renewable, it is, this transformer is the one which can provide a better solution, or a much better solution for integration of renewable energy sources such as PV, solar PV systems, and wind energy systems. This transformer is also very suitable for electric vehicle and fast charging applications. It can be also used for smart grids and in distributed generation systems. So more applications are, these are used in, can also be used in traction system, energy storage, and microgrid. So solid state transformer, as opposed to conventional transformer, is a much smaller, much compact transformer with not only compactness but lot many new features or additional features present in the transformer. A low frequency transformer is a simple system where incoming voltage is either stepped down or stepped up. The control of this voltage is not there unless you imply some type of tap changing. But with the tap changing system, the control of output voltage is also limited because you cannot control the output voltage in a seamless fashion. It can also be controlled in a step. So if there is a step of 10 volt and there is a 5 volt fall, then this tap changing arrangement will give you 10 volt, additional 10 volt, jump, which will be more than the, fall in voltage, which is 5 volt. So you will get 5 volt more. So that is because this system is, it's not continuous, it's a discrete. On the other hand, high frequency transformer will have inherent or inbuilt system where the output voltage will be closely monitored and the desired output will be maintained for an entire you know range of operation. So the if we compare it solid state transformer with the conventional transformer, uh, the conventional transformer is robust, reliable, very high efficiency, and inexpensive because it is not having anything more than the core, binding, cooling system, enclosure, and few certain amount of very very primitive this protection. But the limitation of this conventional transformer is that no voltage and no frequency regulation capability. Uh, Voltage regulation, as I told, is very poor. Power flow is you cannot direct the power to flow in one direction because it flows from the source to the load side only until less you have some active load. But in case of this solid state transformer, we will have capability of controlling the power also. No DC port connectivity. This is very important nowadays because renewable energy systems will require our, particularly solar PV system has DC output, and this DC output cannot be fed directly to the transformer. So that means there is no DC port where the solar energy can be directly fed. You have to convert this energy, solar DC into AC, and then connect it to the grid or transformer. So the structure for a renewable energy integration becomes complex, and this transformer is heavy weight. It has very high weight and consumes a lot of this thing, uh, lot of volume or lot of space. As opposed to this conventional transformer, solid state transformer would be much smaller in size. Size and weight can be reduced by a factor of up to 10. That means 1,000 kg transformer will become 100 kg transformer, and 500 kg transformer will become 50 kg transformer. So this is a huge improvement or huge reduction in the weight and size. That means you can place this transformer. The transportation becomes becomes much easier, and it can be placed in a very small location. It will require very small area. So in the cities where the space is not available, but the space is premium, such type of transformers can be very good or very attractive alternative. So as I told, that power flow and power factor control, fault isolation, apart from the protection equipment, these transformers have their own fault isolation capability, which is due to inbuilt power electronics. So there is a fault isolation within the transformer, and there is a fault isolation or protection system that we have in this in the grid. So that makes it two double. So double protection. That means the overall system will be much more protected as compared to conventional transformer. Reactive power compensation. You do not require additional system in if you have to compensate for reactive power in a conventional transformer. You need additional system reactive power compensators to be deployed there. But in this case, the transformer, solid state transformer itself can compensate for reactive power and seamless control of voltage, and it offers very swift integration of renewable energy sources. So typically the system will look like this. There is a source, there is a transformer, solid state transformer, comprising of input side power electronics, output side power electronics, and the isolation of the transformer is not a simple one. It is a high frequency transformer. So the with the use of power electronics on both sides, we are able to convert or use high frequency transformer in instead of conventional transformer, 50 hertz transformer. And this high frequency transformer will enable a reduction in weight and size. So, what you know, it is this is the technology which is a work in progress. Solid state transformer is not the one which is right now available in the market and being installed. It is used sparingly in many, very few applications, but it has got a potential to replace the conventional transformer and make the overall system more efficient, more reliable, and more, you know, uh, s- uh, smaller, lean. So the traditional coal type of transformer offer longer life and higher efficiencies than it. But the point remains that SST, because of high frequency operation and converter on both primary and secondary side, the efficiency would not be as high as the conventional transformer. So this is the gap which need to be bridged. How to bring up the efficiency of solid state transformer competitive or close to the conventional low frequency transformer. Reliability of SST is low because it has got a lot of power electronics on both in primary and secondary side. So the number of components increase as component count increases. This reliability will also suffer. So there is a need for having more research and testing for these transformers. But nevertheless, there's a lot of work going on converters and power electronics for solid state transformer. So this gap can be bridged very soon. Challenges. What are the challenges? One of the challenges, as I said, is the cost of SST is much higher than the conventional transformer, low frequency transformer. Typically, a 100 kVA SST costs 5 times more than the low frequency transformer. So you can imagine if the cost of transformer is 1 crore, 1 CR, the SST would be 5 CR and investment to the tune of 5 CR, which means 4 CR more, is a huge proposition. It is not so easy. No one will take this issue. Even if it is 1 lakh and the other one is 5 lakh, 4 lakh is also, a big, difference. So design of other important issue is that installation for high frequency transformer is much more challenging because of compactness and high frequency operation. Compactness brings the problem of smaller size, brings the problem of heat dissipation, and high frequency operation brings up the problem of uh, higher stresses on the insulation. So insulation failure due to high frequency PWM waveform reduces life cycle due to electrical stresses and overloads, over voltages, and heating. So these are the challenges, particularly the cost, the installation, and thermal management. These are the challenges which need to be, uh, you know, addressed. As you can see in this figure here, the cost is low frequency transformer, and this the gap in the cost as the kVA rating grows up, gap becomes more and more. You can see for 50 kVA, if the cost is 2.5, then for same with solid state transformer, this becomes about 17 or 18. So this is 6 times or 5 times more. Uh, that makes a lot of difference. But there are simultaneous developments which are going on, and one of the important development which has taken place in the last few years is uh, SiC devices. These devices offer us opportunity to operate the SST converters at very high frequencies. High efficiency can be maintained, converter efficiency can be maintained, And the thermal management also becomes simpler because SiC devices can operate at high temperature. So modular topologies with commercial SI based power devices, the control is complex, and the minimization of volume and weight suffers in that case. But using wide band gap SiC devices, uh, simple converter topologies, the topologies and they have very high efficiency, and the size is considerably reduced. We can also see here in this diagram that why SiC is used, more advantageous as compared to SI. SiC is represented, loss in SiC is represented by blue, and this is, you know, uh, red dot, what you can say is brown is S SI device. So loss is almost 49% reduction in the turn on loss and 90% reduction in turn off loss. So this represents a very significant drop in the loss, switching loss. That means these devices can be operated, SiC devices can be operated at very high frequency without without causing excessive loss. So implying SiC device, SST can it offers simple architecture with 15 kV or 10 kV SiC device. SiC SiC based SST will only need two level and three level converters as compared to multi level converters for SI based devices. So the topologies or the architecture becomes much simpler. SST based SiC devices, for example, if you are using IGBT, which is 6.5 kV, two level converter SST, converter based SST, can only interface with 2.4 kV voltage. So the input voltage can be, it cannot, you cannot go beyond 2.4 kV if you are using 6.5 kV IGBT. Whereas in SiC, if you are using 15 kV or 10 kV SiC with the only three level converter, you need is needed to sustain distribution voltage level. That means 11 kV voltage level can be sustained with a device of 15 kV, as opposed to multi level configurations for IGBT. So SiC MOSFET can significantly minimize the switching loss, and especially the turn-off loss is much reduced. This table also shows how the performance of different devices. So line voltage is 2400. Two level is switching requirement is 6244. Three level is this. So you can see as you increase the level and as you increase the line voltage, the device voltage requirement becomes much higher. I'll have a, give me 5 minutes. I'll come back. Manmohan, 5 minutes, just.
Sir?
Hello?
Yes, sir.
Yeah, please. Okay, I'll start again. So that means, the rating of power rating of devices for 2 level and 3 level for different input voltages. As this is very, quite logical, that to think that as this input voltage increases, the device voltage rating also increases and much faster. For example, if the input side voltage is 13.8 kV, the device voltage requirement would be the rating would be 35.9 kV. So SiC devices, they offer better solution because SiC has larger energy band gap, which is due to which it can operate at high temperatures. One thing. So even if the losses are more, they can operate at high temperature. So you don't need to manage the temperature to that extent. But this high temperature, even if it is acceptable, this high temperature or higher losses that would higher losses would cause efficiency to come down. So this in any case, we need to reduce the losses in this converter so that overall efficiency becomes comparable to the conventional transformer. You can see the device size also here, 6.5 kV, 25 ampere SiC IGBT. Dimensions are 14 into 7 into 4.5 centimeter, whereas the 15 ampere, 15 kilovolt and 10 ampere SiC MOSFET, the size is 8 by 4 into 1.3. You can see volume is drastically reduced. It would be reduced by a factor of, if you can see, 2 to 2, so by a factor of 8. These SiC devices are, as they are coming into the market, hitting the market, it looks that these devices are tailor-made for SST applications, because this is with the arrival of these devices, it is possible to reduce the size of transformer, and that reduction can can accommodate the slight decrease in efficiency. So now coming to the question of SST architecture, what should be? There are numerous possibilities. It is not that you have SST configuration of one type only. The basic premise is that you need you can need to convert input voltage to a output voltage of different level. Now, how you do it, how many stages you introduce, that brings us to the choice of different topologies. So single stage means there is a input voltage, there is a transformer, and there is a converter. Converter and transformer forms the single stage, and there is output. Two stage will have a first input stage, which is rectification. So you have high voltage DC link, followed by another stage, which converts this high voltage DC to a 50 hertz AC. So this is a transformer link here. This is two stage. And then you can have two stage with the uh, LV link, LVDC link, where you have this rectification as well as conversion into lower voltage. So this is LVDC link, and this is the output stage, which converts this DC to AC. Similarly, in three stage, you have independent input rectifier, you have output inverter, and between these two, HV-DC link and LV-DC link, you have a converter and solid state transformer. So this topology, the third one, looks much more flexible in the sense that you have both HVDC and LVDC link. You can connect your renewable energy sources here also on HVDC side or on LVDC side also. And because of the configuration itself, having control at every converter stage, this is much better, much suited application for the application of solid state transformer. But the problem is conversion stages are increased. So we will have to look at the issue from holistic point of view, as to from two things. One, having manageable number of stages so that efficiency is not low, and also having good control. If you sacrifice the number of stages, the controllability suffers. So key features of this one stage, two stage, and three stage are direct AC to AC conversion in the single stage, high efficiency in power density, but limited functionalities. In the second type, DC link is there either on HV or LV side. So this will imply bulky electrolytic capacitors, and this is suitable for integration of renewable. And three stages, you have active rectifier, isolated DC, and inverter. So you have three different stages and more functionalities, but energy storage elements are required in every DC stage, so it becomes bulky. Another beauty or another feature of SST is its capability of modular structure. You can you can create SST cells comprising of converters and high frequency transformer, and these cells could be of smaller voltage or smaller current rating, and then use these cells in a modular fashion to create the desired output voltage and output current levels. So you can see here in the first case, these cells are on the input sides are connected, or SST cells are connected in series. So you can make up the 11 kV by connecting 10 cells in series or 11 cells in series, so that the voltage pressure upon each cell is around 1 kV. And then connect these cells on the output side. You can connect them in parallel so that they can deliver large current. So this is input series and output parallel connection. Similarly, the second one, the input side is in parallel and output side is also parallel. So each cell will need a capability of withstanding the high voltage AC present on the grid side. The third one is input series and output also series. So this will relieve the devices from the input and output side of high voltages. So this looks, out of the three topologies, the first one looks much more, promising, but in certain situations, the second one and third one can also be of some use. So this is how the modular structure will work. Modular structure of direct and indirect, MVAC and LVDC SST. Now you can see here, this is a one cell, this is input side, and this is the output side. Input side is they are connected in series, and output sides are in parallel. And in this side, say in this case, they are connected in, both of them are connected to same source, same supply, and output sides are connected in parallel. So uh, output side in parallel configuration, and here input side in, here input side in series configuration. And we can also form three-phase system by using such modular systems. You can see this is a one module comprising of one converter on the input side, second converter for DC-DC. So these three, and then the isolation transformer. You can convert these connect these converters on the output side. You can connect them in parallel, input side in series, and then form star and delta connections also. For example, here This is a star connection here. This is a three-phase supply, so 10 kV input. Three lines are connected to first converter, second converter, and third converter, and the output of all of them, they are forming a DC link, and this is a DC link here, which is will have individual converters for converting this DC to AC. So this DC link is formed by uh, converters from each phase, and the output side, the AC will be formed again formed by different converters. You can connect them in parallel also and series also. Here they are shown in parallel. So the major issue is, as we say, cost. What contributes weight and cost of SST? You can see the weight of SST is primarily it is because of filters and power electronics. Transformer is very small weight. Heat sink, capacitors, cabinets, and semiconductors, and transformer forms very small portion of the overall weight. Similarly, the cost of material also can see semiconductor forms the major cost component. Other costs are very small. So the solid state transformer is primarily a transformer with lot of power converters, lot of power electronics. So the cost and weight, both of them are primarily determined by the power electronics or semiconductors. And this is where SST, these SiC devices can play important role, because the cost and size or weight can be reduced by using SiC devices. So potential of SST in renewable energy, it can be, SST is can be a key component in future smart grid. It will have multi-port capability, so you can port in different many sources. SST can make the grid intelligent because you have control, you have power electronics. You can imply this default power electronics to create in control, make the system complex, increase and enhance reliability by using modular structure and safety. SST can be used in microgrids or in the areas, because you where the transportation is difficult, you can uh, transport these small components, small size SSTs very easily. Uh, as I told, as we discussed, SST is a very good solution for renewable integration, and it will also offer reactive power support, because there are power electronics converters. So reactive power compensation is default in SST. That means the conventional transformer, where you require some sort of reactive power compensation, additional reactive power. Here in this case, it comes as a part of the SST. Harmonic mitigation, harmonic because of power electronic systems, you can mitigate, not only mitigate for the harmonics present in the load supplied by the SST, but you can also mitigate for the other harmonic present in the input side. So it can mitigate voltage swells and sags. It can, as I said, that it can also uh, improve the power quality, protect against the short circuits. This is a protection because of the control of converters. You have another stage or inner stage of inner layer of protection. Faster control response to the fault uh, management, and can handle the instabilities of main grid by compensating for the power quality. So typically, where can you place this solid state transformer? Now, if we talk about AC microgrid architecture, then the AC microgrid architecture looks like this. You have main grid, a transformer, and then you have this microgrid here, which is connected to battery energy storage, which is connected to the renewable sources through converters, and you have AC load, you have DC load. So there is a transformer here at the AC microgrid which connects it to the main grid, apart from the distributed energy generation sources. If we use solid state transformer, then this can change. How can it similarly for DC microgrid, we'll see later on, but uh, DC microgrid also unit transformer and then converter, and this is a microgrid. You can connect your renewable energy sources, battery energy storage, then supply DC loads directly and supply AC load like this. But in case of SST based system, how will it look like? In SST based system, the system would be, the overall system will become much simpler. Now the grid connection is through solid state transformer. So solid state transformer here will have both AC bus and DC bus. So AC microgrid and DC bus will have connection of PV, connection of batteries and other renewable sources, and you can supply DC loads directly. And this would be the microgrid. So microgrid formed here is integrated through a single transformer. So if you compare it with the previous one, the converters here are much smaller. Number of converters here is much smaller as compared to the number of converters that we had here. You can see here. Similarly, if you use this type of solid state transformer topology, which is three stage, then you have HVDC here, LVDC here, and solid state transformer, high frequency transformer and output stage. So brings you, this gives you an opportunity to form a DC grid, and this makes makes the AC grid. So you can have mix of both AC and DC microgrid. You can connect your loads, AC loads here. You can connect your DC sources here. So this solid state transformer will give us direct connection of DC sources, batteries, and PV cells to the transformer. You don't require, except for the voltage level change. If you do not have voltage level change, you can directly connect them to the uh, DC link, low voltage DC link. Then how can you, as I said, that this solid state transformer is also a good option, a potential option for fast chargers. In fast charger, what you need is a DC-DC converter. What you need is a supply, AC supply. So AC supply here in the traditional fast charger, you will have HV, AC-DC link, and then DC-DC, which is the final charging stage. In case of SST-based fast charger, what we can do is we can provide this, this is a HV AC to DC conversion. Then this transformer can, this solid state transformer becomes part of our DC-DC converter becomes part of solid state transformer. And what you need to install is only solid state transformer, which is fed from this HV DC. Similarly, this can also play an important role in traction, where low frequency transformer, if it is used, if you apply low frequency transformer, this is a typical diagram of uh, railway traction system. AC supply is equal to DC. Then you have line frequency transformer, and this is a DC link. Then DC to AC conversion for motor. Now what you can do is you can convert this thing into replace this by a solid state transformer, and uh, this stage also can become part of solid state transformer, and even this stage also. So additional converters which are required, they are in the form of converters present in the solid state transformer, and the weight of this would be reduced drastically. And this reduction in weight will brings in a lot of uh, positive change, because this traction transformer is placed in the locomotive. So if you are carrying, instead of 1000 kg, if you are carrying 100 kg transformer, it makes a lot of difference. Similarly, if it's a wind energy system, conventional one would be like this: generation, capacitor bank, transformer, and then STATCOM also. And here it would be generation directly through solid state transformer, it will be interfaced to the grid. So you don't need all this in STATCOM and other things. And before I close, I'll discuss one or two systems that we have developed in IIT Roorkee, solid state transformers. So we will see we are using SiC based devices and dual active bridge configuration. So this is DAB based DC-DC converter for renewable energy integration. You can see here, this is the DAB converter, dual active bridge. So there is a single phase bridge on the input side, there is a single phase bridge on the output side, and there is a transformer, high frequency transformer here. So we can connect individual sources. What you need to do is, if it's a grid, you can connect that grid here, DC supply. If it's wind turbine, you can convert this to DC, connect it here. Solar, it's DC, connect it here, and so on. And similarly, output side also, you can feed different loads either directly through the available DC here, or you can convert this into desired, level of output. So this will have high frequency and high frequency, high efficiency, and bidirectional power flow. Here you can not only the power will not only flow from input side to output, but it reverse power flow is also possible through this solid state transformer. Leakage inductance of transformer is control the power transfer and soft switching to achieve soft switching of the converter. And both buck and boost operations are possible. It has symmetrical structure, so input side and output side looks similar, so the control is more or less similar. And there is a galvanic isolation as is required in the case of transformer. There is a isolation present here. So this scheme shows that how a single solid state transformer can be used to connect so many things and control them from one location. So about DAV, dual active bridge converter, this is the input stage. It's a two-leg converter having four devices, and input side is DC supply. So if it is coming from the grid, then there is a rectifier on the input side. And then there is a high frequency transformer. And similar to the primary side, you have another stage out secondary full bridge. So this is primary full bridge, this is secondary full bridge. And output is DC. So if you want to convert this to AC, you put an inverter here. So put a rectifier here and put an inverter here, and then and the DAV here. So there are three things: input rectifier, output inverter, and DAV. That will form a solid state transformer, a typical solid state transformer having DAV converter. So the strategy here is to create phase shift. So single phase shift modulation technique. There are different methods of controlling DAV, and one of the simplest method is SPS modulation techniques, which is shown in this diagram. And this is the developed can see this is a 5 kilowatt setup. It's very small. You can, this is a 5 kilowatt transformer which you can hold in your hand. You can just put it in your hands. So it has 5 kilowatt output, whereas conventional 5 kilowatt transformer will also be very heavy. It will be a box of the size of few feet in height, few feet in width, and depth also. But here it is the overall system. We have been not commercialized it, but still the overall system is dimensions are every dimension is less than 1 feet. So the input voltage we have made this right type for 400 volt DC and 200 volt output is DC. We have used 50 kilowatts switching frequency. These are the waveforms of primary and secondary winding voltages, and this phase shift within them is responsible for power transfer. So how you manage this phase shift? You can transfer the power from input side to output side or vice versa. And these are the currents, winding currents. These are the simulated waveforms, and these are the experimental waveforms. This is the temperature rise, the different parts of the transformer. Uh, this is for temperature. The major issues that we are, tackling are ZVS, how to make Z-based operation of this DAV converter over a wide range of output currents. And as you can see here, there is the current in the transformer is there are spikes, So these spikes in the current creates problem in the form of, higher peak leads to more conduction loss and loss in the transformer. So the major issues that we are tackling are how to make this ZVS range wider, how to reduce this peak current, and how to create seamless transitions of this operation from different loads and reduce the copper and core losses of the transformer, and also minimize backflow. This DAV converter based transformer has a problem of backflow power, which will require higher power, forward power. So this backward power flow is not contributing towards the power flow. So these are these figures show different modulation techniques. SPS single, SPS we have single phase shift, extended phase shift, and dual phase shift. So we can see here the backflow in this case is more. In this case, it is reduced. Second case and third case. So second case is much smaller as compared to all of them. But there is a significant improvement in the backflow power as compared to the first case. And the peak current is also reduced in both these cases. So the comparative analysis of different modulation techniques. This complexity is more in EPS and dual phase shift. ZBS range is limited in first case, SPS, and it is extended in all other two cases. And backflow power is large in first case, small in the other two cases. So similarly, high current stress in the first case and other two cases low. Efficiency with that reduce the efficiency also. In the next two cases, it is high. So I think that's one more. I think can I close it because it will take much more time.
Sir, if you spend 5 minutes, that's okay. Otherwise, we can close here also.
Okay, so I'll discuss one more. Okay.
We can extend 5 minutes more.
So one more system that we have developed is seamless dual mode control of DAV. Here, we have two control variable which are used to develop the control strategy, and this control is much simpler. And what it leads to, two modes, operating modes are used to achieve ZVS operation with low current stress for entire range of load. So in loading conditions, as loading conditions change, uh, this ZVS operation is maintained for all loads. The transition between the mode transition is seamless, and junction capacitance of switch and nitration inductance of transformer are used to develop the control strategies. So these are the two modes of operation uh, of this. Operating mode 1 and 2 are used to develop the control. Primary and secondary voltages are square waves, and true control variable are sigma and D. Those are defined. So this is the peak transformer current comparison uh, as compared to the existing one, EPS, PS, and DPS. This proposed strategy gives much lesser peak current for different conversion ratios, and similarly for this is the peak current for different power ratios. This was the developed system. This again 5 kilowatt. You can see the size of the system, 5 kilowatt system. We have, even though it has not been packed for a professional, industrial system, but still you can see 5 kilowatt transformer looks of the size of pen. One dimension is this much, and the other vertical dimension is also this much. These are the experimental results. You can see the peak current is reduced. It is not spiky as it was earlier. Okay, so this is a different another type AC. So I think Manmohan, I'll close here because this topology discussion on this will take another half an hour.
We can stop
So
here, sir. Any
Manmohan,
query? Ji, sir. Any query from any participants? Please let us know.
how many participants you have?
Sir, right now there are less, but around 60, 70 we have registered participants.
Achha, all of them are online?
Online, yes, sir. All are online. Sir, one query, which SST is better? One query in chat box, sir. Sir, I'm audible.
Yes, please.
सर चैट बॉक्स में क्वेरी है विच एसएसटी इज बेटर
दोबारा बोलना
विच एसएसटी इज बेटर
SST are, it will depend upon the application. If you do not require DC link, then you can use, DAV can be used. If you require DC link, then you have to go to multi-stage system. And that would also depend on which type of DC link. If you require high voltage DC link, then you have different approach. If you want low voltage DC link, different approach. So SST configuration, there is not a singular situation. It will depend upon the application, whether you require DC. It can also be used for DC, charging. As you can see here, this one, this previous one, I'll show you. So, yeah, this one. Now this is DC, and the output is also DC. So this is suitable. DAV type of topology is very suitable for charging, because input side DC, you have a charger, getting supplied from the grid, so that is rectified, and then you do not need this in output side inverter. So DAV is suitable here. But in case you need inverter or AC output, then you will have to have another converter here, or you can also have a topology which forms integral part of the SST. So there are many topologies which are can be used, and it depends on the application.
So I hope this suits answer to you, Mr. Chandrasekhar. Any other query? So I think no much query. Sir, I have just one query that SST is nowadays very much popular in research, but the basic fundamentals remain same. Like it's kind of a conversion of AC to DC, DC to AC, and non isolated converters. That fundamental. So, means why it is suddenly boom?
This is a question for me, or you are answering?
Sir, no. I'm asking, sir, this question.
Achha, what is? Please repeat it.
I'm saying the basic fundamental of SST is like it's a controller only, AC to DC, then DC to AC kind of things. So those things were
It is
known.
a system where the transformer is accompanied by a converter on both input and output side.
Yes, sir.
So the transformer, conventional transformer, is only a core and winding, whereas here you have core and winding in the form of high frequency transformer plus lot of power electronics.
हाँ सर, मैं वही पूछ रहा हूँ सर कि सडनली अभी मतलब पिछले 5-10 साल में बूम में आया है ये कंसेप्ट. तो दिस कंसेप्ट्स आर ओल्ड ओनली, सो इट कुड बी डन अर्लियर
This
एज वेल.
concept is not new, but this concept is now finding applications because of charging system, charger में, EV charger.
हाँ.
Because of SiC devices, now it is capable, it is coming close to the efficiencies of conventional transformer.
Okay. Because of SiC GaN devices. Okay. Okay, sir. Thank you.
Okay, thank you.
I think there is no more questions, so we close this talk over here. So we are very much thankful to sir that he has delivered a nice talk on SST, which is a very important research topic nowadays, and gave various ideas about this. I hope that these ideas will help the participants to flourish their research and other things. So thank you very much, sir, for being with us and delivering a nice talk. Thank you so much.
Thank you.
Thank you, sir. Okay, so with this we end the today's sessions, and now today was day 8 for us. So tomorrow we will have 2 talks. That one will be given by Professor B.L. Narasimha Raju, and the other by Professor Deepak Fulwani from IIT Jodhpur. So both talk, one will be in morning, one will be in evening, and followed by the quiz. Then 3:30 around we will have quiz. So that's for tomorrow. And day after tomorrow we will have 2 more talks. That is with me only. So with that we will complete our FDP. So thank you all for being with us for last 8 days. It is a wonderful journey with all you. Thank you.